So this is lecture 11. And it's on Chua's circuit. So our electrical engineer isn't here today. So his car got stuck, for Lucas, his car got stuck in the middle of Newark. So that's why he couldn't come today. Which is why we need you guys to finish up the electrical engineering part of it. But so since he's not here, I'm gonna have to ask you guys these electrical engineering questions. So it might be somewhat more interesting since some of you may not know, know it fully well, I guess. So we can kind of feel around for what the answer should be. Okay, so Leon Chua designed the circuit that basically produces a strange attractor that's very similar to that butterfly, to the Lorentz strange attractor. So that's kind of what he was going for, and he wanted to create something very simple that does that. So this is the circuit he came up with. So I think I'm going to color code this. So it's kind of like this. So that's an inductor. And then it goes into, so there's a capacitor here. Actually, let me use red for this. Then there's a linear resistor over here. And another capacitor. And then we're going to have a nonlinear resistor, which is what really drives the chaos. So here is the nonlinear resistor. So that's the nonlinear resistor. And that's what's going to drive the chaos. So this is, let's call this NR. This is just going to be R. And then let's say this is C1. This is plus, minus. This is, so this has some voltage difference of VC1. This one's going to be C2. And it has a voltage difference of VC2. And then this one's going to be, say, call it, so this is going to have a voltage, or an inductance of L, and it's going to have a current going through it, say, IL. And then that's basically it. So we also have this connected to ground. So we have a circle like that.
How do you, what does a nonlinear resistor essentially imply?
So we'll talk about that, but maybe we'll talk about it first. So basically for our nonlinear resistor, we're going to make it or we have made it out of op amps. So we basically use potentiometers to replicate this nonlinear resistor. But it's basically like this. So it's a good thing to talk about it now. So let me ask you this. So for a linear resistor, what is the current in relation to the voltage?
It should absorb something, right? So it should be.
Well, yeah, got it.
Well, it should be less than, right?
No. So what is the? How do we write that equation? That's what I mean.
V equals IR.
Okay, V equals IR. So that means I is going to equal
V over R.
1 over RV, right? Where the sub R is just representing that resistor. So that's a linear resistor. So here the relation is linear. So that current that's going through that resistor is related to the voltage drop, right? And this is just the constant, the proportionality constant. So it has a linear relationship. However, with a nonlinear resistor, it's going to be something like this. It's going to be nonlinear, obviously. So nonlinear resistor is going to be IR equals G of VR, where G is some sort of nonlinear function. With the Chua diode, with Chua's nonlinear resistor, it looks something like this. It looked like a piecewise linear function. This is V, this is I. I should probably call this G of, so I equals G of V. I'm going to call it that. And it had a relation like this. So this is what the function looked like. So it wasn't quite linear. It has 3 linear pieces, so it's piecewise linear, but it's not linear.
All right.
So that's what the nonlinear resistor is. So now we have to come up with some equations for this. And what type of, so obviously we're going to come up with differential equations, but what type of differential equations do we want to come up with? Like what order?
I guess in second.
Not quite. So why second? What was the thinking behind second?
Because you want to see, I guess, like the change in like the voltage, I guess, and like the.
Okay, but so what's the first circuit that you learned to model?
First circuit.
Yeah. So in differential equations, what did you learn to model? So it was the RLC circuit, right? So you have a resistor, you have an inductor, you have a capacitor, and you have a voltage source, right? So that would be second order. So that's probably why you were thinking second order, which is a good guess because that's, you know, the RLC circuit is kind of the most basic non-trivial circuit that you kind of learn of in differential equations. But for the sake of analysis, what do we want the equations to be? In dynamical systems, what do we want them to be?
First order.
So we want all of them to be first order, right? So we want to come up with some first order equations. And whose law are we going to use for circuits? What's his name?
Kirchhoff.
Yeah, so we're going to use Kirchhoff's law, right? So we can use 2 laws. One says that if you're in a loop, then all the voltages are going to add up to 0. And another law says that if you're going into a node, then all the currents are going to add up to 0, right? So it's Kirchhoff's current and voltage laws. So if you're in some sort of loop, then all the V's, the sum of V's equals 0. And then if you have a node and you're going into some node, then the sum of all the currents are going to equal 0, right? So it's Kirchhoff's current and voltage laws. So it's just a conservation law, right? So you're not getting you're not getting current out of nowhere, you're not getting voltage out of nowhere, right? So that's the idea. So first we can look at, say, this part. Do we want to use Kirchhoff's current law or voltage law? So in order to know that, we have to know the relation between voltage and current for an inductor. So do we remember what that is?
Times it's physics too.
Yeah. So okay, so is it the derivative of current times something equals the voltage, or the derivative of voltage times something equals the current? Because we want first order equations, right?
Oh, is the derivative of voltage equal to current?
Not quite. So that's true for the capacitor. So for the capacitors, we take the derivative of voltage, and that's going to give us a current. But that's not quite true for the inductor. So for the inductor, it's going to look like this. It's going to be L di dt. So let me just write this as IL, just so we're clear. Is going to equal what? So we want the voltages here. So this is the voltage for the inductor. We want the voltages here to equal 0. So what elements do we have in this loop?
Inductor and capacitor.
So it's going to depend on the second capacitor, right? So it's going to equal what for the second capacitor? It's the simplest answer you can come up with. It's right on the board.
V?
Right, so it's going to be negative V, right? Negative VC2. So that's going to be for that first loop. So we want the voltages because it's because of the di dt equals the voltage. So di dt is going to give us our first order ODE. Now, what do we have for the capacitors? So as we said before, it's going to be dV dt equals the current, right? Or something times the current. So since we get a dV dt equals something times the current, do we want to use Kirchhoff's voltage law or current law? So dV dt equals current.
So the current.
So it's going to be the current law, right? So we want the sum of currents, right? And one of the currents is going to be represented by dV dt. So that's the idea. So we want the current where, though?
The resistor, right?
Well, we want the current in this node, right? We want the sum of currents that are going to this node. So that means we get this current coming in, we get a current here, and then we get this current coming out, right? So the current here is going to depend on this and this. So we can very easily write this. So that current is coming in. So really over here, I should have written it like this. This would have been better if I wrote plus VC2 equals 0. So that would have been better. So here we get this current coming in. So IL is coming in. And then we get this current coming out, so it's minus what? What's the relation between that, the voltage and the current there?
So it should be minus C2 dVC2 over dt.
Okay. And then how about here? What happens with that current there?
Also minusing R for me, right?
Okay, so we can have minus 1 over R, right? In order to get that, the current, right? So 1 over R times what?
So it should be times VC2.
So it's actually going to be VC2 minus VC1, or is it the other way around? Let me just check. So it's VC1 minus VC2. Equals 0, right? So those capacitors are going to create a voltage difference. And that's going to drive current through the inductor. So you have the voltage drop here is going to be VC2 minus VC1, but then the inductance is going out of that node, right? So the, sorry, not inductance, the current. So the current through the inductor is going into that node, and then the current across the resistor is going out of that node. And then the current is going out of that node that way. So we get that. So we should get the same sort of stuff for this, right? So we don't have this anymore, but we still have a current for the capacitor. So that's going to be minus C1 dV C1 over dt minus 1 over R. But now this is the other way around, right? So this is going to be VC2 minus VC1. And then what else do we need? So there's a current that is, we can think of it as coming out of here because it's VC2 minus VC1. There's a current coming out of here, but how about what's happening on that other branch?
Should current be coming out of it, or?
Well, that depends on the nonlinear resistor, right? So the nonlinear resistor we call G of VR. So that's how we're going to write it. So it's actually going to be
G of VC1.
exactly G of VC1. So because that's the only thing causing a voltage drop here. So this is going to be, we're going to write it as minus G of VC1. And I believe that's just for convention. Let me just make sure I have everything correct. Actually, this should be plus. Yeah, this should be plus, but that's just convention, and then that should be plus then. So yeah, those two should be plus. And then I believe everything is correct. Or is that one minus? Okay, yeah, by convention, it looks like this is minus. But we can make it plus, it doesn't really matter. So this depends on how we draw this curve. So then over here, we're thinking of the current coming out as 1 over R VC2 minus VC1. But since we have VC1 minus VC2, we put a plus. Okay, so this is the equation for Chua's circuit. So it's not too complicated. And it looks like it can give us chaos because it's three-dimensional, there's a nonlinear element, so it seems like it can give us chaos. And if you actually go ahead and plot this, you can see that it looks chaotic. Now, to prove it, there are a few different ways. I don't know if anyone actually proved it in the classical sense, but I do believe that someone used something called topological entropy. So they put this into the computer and you can estimate the topological entropy of it, and then you can say, oh, this is, chaotic. But I don't know too much about topological entropy. There's someone at Rutgers who does a lot of that stuff, Mishaikov, who is really big with the topological entropy. So he's quite an expert in that. I don't know too much about that, though. So there are ways that we can show it's chaotic, but I don't think it can be shown classically. That might be more difficult to show. Okay, so that's Chua's circuit. Since it's not quite so easy to analyze, we're not going to analyze it here, but let me tell you a bit about the work I've been doing. So in recent years, people have taken the Chua circuit and they've implemented NOR gates, and they've also implemented the RS flip-flop. So let me tell you something about NOR gates and the RS flip-flop then. So this is how we represent a NOR gate. So whenever you see this, it's going to be a NOR gate. And let's say the inputs are X and Y, and the output is F. So since this carries out a logical operation, we can put a truth table to it. So let's say we have X and Y, and then we have F here. So then if it's 0, 0, so if both inputs are 0, it's going to be 1. And then for all other inputs, it's going to be 0. So that's why it's called a NOR. Except I should put 0, 1 here, just to be, just to keep with the binary. So these inputs are going to be 0. So that's why it's called a NOR. So it's basically, so the OR gate, with the OR gate, if you have either of them as 0 or either of them as 1, so if you have X or Y as 1, you get 1 as the output. So that's the OR gate. And that makes sense. Like, that's the logical operation, right? So you have this or that, which means there's something. So that's the OR gate, but then the NOR is that inverted. So that's basically why if you have 0, 0, then you get a 1, and then for everything else you get a 0. So it's just the OR gate that's inverted. So we get this as a truth table, and then from this we can create something called the RS flip-flop. So the RS flip-flop looks like this. So it's with 2 NOR gates. And this is one of the first flip-flops to be invented. And this is Q. So let me actually write this as S and R. So this is R. This is S, this is Q prime. So the idea of the RS flip-flop is that you can set a bit or you can reset a bit. So if S is 1, then you're setting a bit, basically. If R is 1, then you're resetting a bit. So that's the idea, except it gets a little bit more complicated than that. So we'll draw that in the truth table. But the reason this was created was so that you can store things in memory. So that's the idea of this. So basically, if you have it set, then you're storing that bit in memory. If If you have a reset, you're resetting the bit, but it's still being stored. And you can use this to create adders and things of that sort. So you can create some very primitive binary adders. So this was very useful early on. Later on, we got different types of flip-flops, but this is what it basically acts like. So you have S and R, and it's going to be Q, this is Q prime. So if you have 0, 0, then whatever the last state of the bit was, it's going to stay as is. So it's just going to stay as Q and Q prime. So let's say you have 0, 0 there. If you have 1 there and 0 there, it's going to just stay like that. It's not going to change. If you have 0 there and 1 there, that's what it's going to be. It's not going to change. Now, if you reset the bit, then this is going to be 0, and then Q prime is going to be 1. If you set the bit, then Q is going to be 1, and Q prime is going to be 0. Now, the reason why this stopped being used was because of that 1, 1 state. So if you have 1, 1 coming in, then it's going to go to 0, 0. But now if it changes from that, so say you have 1, 1 coming in, these two become 0, but then it changes, then something called a race is created. So that depends on, so there's always going to be some sort of lag. So what these two bits are is going to depend on that lag. So you can't predict it. So if you have it at 1, 1 and you change it to something, you can't predict what it's going to be. So this is a reason that people stopped using this in industry and people started using other types of flip-flops. But in recent years, people have taken the Chua circuit and implemented the NOR gate and RS flip-flop. But now, because of that inherent unpredictability in the NOR gate, when they created these, in the RS flip-flop, when they created these circuits out of Chua circuit, they saw things that looked chaotic when these were both 1. So yeah.
So how do you implement this into Chua's circuit?
So I don't know too much about the electrical engineering of it, but basically what they do is they take Chua's circuit and then they put, so they can create a NOR gate with it. So they take Chua's circuit and then they use this threshold. I forget what it's called. Threshold something, some sort of thresholding device that will limit how much the circuit can increase, or the voltage can increase. And then it'll feed that information back to Chua circuit. And then it'll do that thing. So it has some sort of feedback where it tells it that it can't go beyond the point.
The voltage it changes, essentially.
Yeah.
It forces it changes.
Exactly, yeah. So it forces it to drop down to some point. So if you have the usual cases, it's fine. But then if you have 1, 1, it keeps wanting to go beyond. So even though the threshold is dropping it down, it keeps wanting to go back up. And you can't predict how much it's going to go back up. But then at some point, you can threshold it so that it stays. So say if you're at 1, 1 here, you can threshold it so it stays at 0, 0. But now the threshold voltage is going crazy. So that's what I've been looking at. So I wanted to model how that threshold voltage acts. But of course, since Chua circuit is so difficult to analyze, you're not going to be able to analyze this sort of thing using ODEs. So that's why we wanted to analyze it with maps. So we came up with models, discrete dynamical models for this, and we wanted to see how the threshold acts if we can model the threshold. And we wanted to model it for the 1-1 case. So that's basically what we concentrated on. So we got that done, but now what I want to do for that final portion is come up with a model, which I have. I have come up with a model, but now I have to actually really analyze it. But come up with a model that replicates the behavior seen in the experiments. Very, well, not precisely, but more precisely than our other models have. So our other models only modeled the 1-1 case. That's what we basically wanted to do. So that's, our other models did that. But now what I want to do is, where in experiments they change it from different voltages. So they just change from each of these states to show what it's doing. I want to do the same thing with our model and just keep changing it and then show that it changes just like in the experiments. So that's basically what I've been up to now. So I'll tell you about how we modeled that. So basically we come up with a model for the NOR gate itself. So this is the type of model we come up with. So here it's Boolean algebra. But now let's say we have something like this. 1 minus some phi of x times 1 minus some c of y, where phi of 0 equals c of 0 equals 0, and phi of 1 equals c of 1 equals 1. So if we come up with a model like this, when x and y are both 0, then it's going to act just as the regular NOR gate does, right? So if that's just both 0, then f is going to be 1. And then at any other case, it's going to be 0. So it acts just like the NOR gate, except now because we have this, it's called a threshold control unit. That's what it's called. So now that we have Chua's circuit and we have this threshold control unit, we're going to keep what happens in between arbitrary. Or arbitrary up to until after the analysis. And then the analysis is going to tell us what it may look like. So that's the idea of it. So we keep what happens in between kind of relaxed. We don't set it, and then we try to figure out what that should be. So whatever is in between is going to depend on the components of the Chua circuit used. So that's highly sensitive. So that's why we wanted to keep it kind of arbitrary and then see what happens. So we wanted to see what sort of functions will allow it to be chaotic, basically. So that's what I've been doing. And let's see. So yeah, we basically have results that give us something qualitatively similar to the experiments for the 1-1 case, but now we want to do it for all cases. So that's the sort of stuff I've been doing with Chua circuit. So any questions about any of that?
So is the RS flip flop is a chaos part of the system, or
What do you mean?
like the chaotic resistor?
Oh, the nonlinear resistor?
Yeah. Like,
So the nonlinear resistor is used in Chua circuit, and then they just make these using Chua circuit, basically.
okay.
So the nonlinear resistor is what drives the chaos. But this unpredictability at 1-1 is where we see the chaos, basically.
So the RS flip-flop isn't chaotic by itself?
No, it's not. No.
It's just where chaotic properties tend to propagate?
That's basically where, that's the parameters for which we see chaotic dynamics. So yeah, the RS flip-flop itself isn't chaotic. It might be unpredictable, which gives us, I guess it guides us to this 1-1 case when we make it from Chua circuit.
And do you model the RS flip-flop as well, similarly to how you modeled the NOR?
Yeah, so we basically wanted to come up with models for all the gates and then model the circuits. So I came up with models for every single gate, and then we can use it to model the bigger circuits. So now this will work no matter how many NOR gates we use. So we can have like a 3-dimensional RS flip-flop, and it would still work. So we did that, but like with just linear circuits, with circuits without any feedbacks, then I mean the model obviously holds for that. It acts just as you would expect it to. So I shouldn't say the RS flip-flop isn't chaotic. The usual way it's constructed, the usual way it's implemented is not chaotic. But it depends on the sort of...
So the regime that's normally used in isn't chaotic, but
No,
specific regimes it could be?
So okay, usually it's made with semiconductors, right? And it depends on what sort of model you're coming up with. And electrical model is not going to be chaotic because it's just Boolean algebra. But now, I mean, you can come up with like a chemical model of how the concentration of the semiconductors are changing, right? So that might be chaotic. But that's difficult to come up with. That's not very trivial. But now with this sort of implementation, where we use Chua circuit, we get something that acts as an RS flip-flop would, but we get chaos in the electrical sense. So we basically have these equations floating around.
So the general idea of Chua circuit is to prove that chaotic properties can be exhibited in electric systems?
Well, Chua designed it just to show a very simple electrical chaotic system. So he just wanted to come up with a system that was chaotic, that used just very regular electrical components. So any other questions about that? So if there are no more questions, then we can try to get the circuit to work.